everyone, welcome you all in my YouTube channel Engineering Guru 29. In this video, we will cover Carnot cycle, assumption of Carnot cycle, then four process of Carnot cycle, and then limitation of Carnot cycle. So let's see one by one. Carnot cycle. In 1824, Sally Carnot, a French engineer, has introduced an ideal cycle which consists of two reversible isothermal process and two reversible adiabatic process. The important thing, Carnot cycle is the ideal cycle and consists of two isothermal process and two adiabatic process. So there are some assumptions in working of Carnot cycles. The first one, the working fluid is a perfect gas. Then second one, compression and expansion process are reversible. So whenever we use this Carnot cycle, or we can say this ideal cycle, we assume this following terms, means the working fluid is perfect gas, working and compress expansion process are reversible. Then the piston cylinder arrangement is weightless and does not produce friction during the motions. Fourth, the wall of piston and cylinder are supposed to be perfect insulator of heat. The cylinder head is so arranged that it can act perfect heat conductor or perfect heat insulator when desired. The transfer of heat does not affect the temperature of source or sink. So these six assumptions made in working of Carnot cycle. So in exam, the question may be asked, write down the assumption of Carnot cycle. So you should remember this. Now focus on main part, that is following are the four processes in Carnot cycle. Now let's see one by one. First of all, understand the Carnot cycle. Here this is the cylinder with the perfect insulator. So this is one assumptions, the cylinder with the perfect insulator. Here this is the working fluid. This is the heat source T1, this is the insulator, and this is the heat sink T2. Now understand the first, that is isothermal expansion 1, 2. The heat source is contact with the cylinder head, which is contact with the cylinder and which is acting as a perfect conductor. The air expands at the constant temperature T1 and constant temperature T1 from V1 to V2. The isothermal expansion is represented by the curve 1, 2 on PV diagram, that is figure A, and TS diagram in figure B. The heat supplied of the system during the process is Q1 is equal to the work done. Now understand how can it work in PV diagram and TS diagram. In this image we can see that on x-axis, that is the V, that is called volume, and on y-axis, that is pressure. This diagram is called PV diagram, and here on x-axis, that is S, entropy, and y-axis, that is temperature T. This is called TS diagram. Okay, now understand how can this isothermal expansion work. This is for curve 1, 2, means this point 1 and point 2. This is in TS diagram, point 1 and point 2. The heat source is contact with the cylinder end, which is the contact with the cylinder end, which is acting as a perfect insulator. The air expands. Here the air is expands at constant temperature T1. Here you can see that this is the temperature T1. So here from point 1 to point 2, the temperature T1 is constant and volume V, V1 to V2. Here this is point 1 V1 and this is point V2. So this is called isothermal expansion. The isothermal expansion represented by the curve 1 and 2. The heat is supplied to the system during this process Q1. here this is the Q1. The Q1 is heat supply during the process and is equal to the work done. The work done Q1 equal to W112 equal to P1 V1 log E V2 by V1, or we can write MRT1 log E raised to R, where R equal to expansion ratio V2 by V1. So this is the isothermal expansion process 1-2. Now let's see the second process, that is adiabatic expansion 2-3. The heat source is removed from the cylinder end and the insulating cover is brought in the contact. The air expands reversibly and adiabatically from V to V3. The reversible adiabatic expansion is shown curve 2-3 on PV diagram and TS diagram. The temperatures fall from T1 to T2 since no heat is absorbed or rejected by the air. Now understand in figure, we can say this is point 2 and this is point 3 in PV diagram. In TS diagram, point 2 and 3. So this is adiabatic expansion. We already discussed that there are the two expansion process and two compression process, means isothermal expansion in 1-2 process and adiabatic expansion in 2-3 process. The heat source is removed. So during the adiabatic expansion, heat source is removed from the cylinder end and insulating cover is brought to contact. The air expands reversibly and adiabatically from V2 to V3. So here this is point in PV diagram, this is point V2 and this is point V3. So during this process, air expands and reversibly and adiabatically from V2 to V3 like this. The reversible and the temperature falls T1 to T2. Here you can see that this is, so temperature is fall from T1 to T2 since no heat is absorbed or rejected by the air. The work done by the air equal to P2V2 minus P3V3 divided by gamma minus 1. Now third step, that is isothermal compression. The insulating cover from the cylinder end is removed. The cold body heat sink at the temperature T2 is brought in the contact with the cylinder end, which is now good conductor of heat. The air is compressed at constant temperature T2 from the V3 to V4. The isothermal compression process is shown curve 3-4 in PV and TS diagram. So in diagram we can see that this is point 3 and this is point 4, and in TS diagram this 3 to 4 point. Now understand, the insulating cover from the cylinder head is removed and cold body at the temperature T2. So here at point temperature T2 is brought in contact with the cylinder end, which is now good conductor of heat. The air is compressed at the constant temperature T2, means here the temperature is constant. So here temperature is constant. Now in process 3 to 4, temperature T2 is constant and V3 to V4. So this is called isothermal compression process. This curve 3 and 4, it is called isothermal compression. So process 1, 2 and 3, 4, it is also called constant temperature process. So the heat is rejected by the cold body is given by, you can see that here in process, during process 3 and 4, the heat is rejected. In process 1, 2, heat is supplied during the process 1 and 2, but in 3 and 4 heat is rejected. So T2 equal to W34, or we can write P3V3 log V3 by V4 equal to MRT2 log R, where R equal to compression ratio V3 by V4. This is same as we already see in isothermal expansion. For the closed cycle, expansion and compression ratio are equal. So we can write R equal to V3 by V4 equal to V1 by V2. Now, final step, that is adiabatic compression. The cold body is removed and insulating cover is brought in contact with the cylinder end. The compress reversible and adiabatically from V4 to V1. The reversible adiabatic compression is shown by curve 4-1 on PV and TS diagram since no heat is absorbed or rejected by the air.
First open YouTube and write down Engineering Guru 2020. Search. This is Engineering Guru YouTube channel. Open this and subscribe this for more update. Various playlists available here. You can see this is for various subject. This is for velocity diagram, uniform velocity, for cam profile, synthetic linkages, and more video, more playlists are here.
Now in image, or we can say in diagram, we can see that this is the adiabatic compression. So curve will go from V4 to V1, V4 to V1, and here in TS diagram the curve 4 to 1. So the cold body is removed and insulating cover is brought in contact with the cylinder and air is compressed. So that's why it is called adiabatic compression, and adiabatically from V4 to V1. So pressure is raised due to compression. The reversible adiabatic compression is shown by the curve 4-1 since no heat is absorbed or rejected by the air. In this diagram, we can see that 2 isothermal expansion means curve 1 is isothermal expansion, curve 2 is adiabatic expansion, 3-4 isothermal compression, and 4-1 that is adiabatic compression. Work done and air equal to P1V1 minus P2V2 divided by gamma minus. So in PV diagram we already covered. So curve 1 and 2 isothermal expansion and curve 2 to 3 that is adiabatic expansion. So two expansion process during process 1, 2 and 2, 3, 3, 4 and 4, 1. 3, 4 is the isothermal compression and 4, 1 adiabatic compression. So two expansion process and two compression process. So heat is supplied during the curve 1 and 2, we can say during the isothermal expansion, and heat is rejected during isothermal compression. So this is the 4 main process in Carnot cycle. We also observed that during curve 1 and 2 the temperature is constant, and during curve 3, 4 means during isothermal compression the temperature T2 is constant. So it is also called constant temperature process during 1, 2 and 3, 4. But in curve 2, 3 the pressure is dropped, and in process 4, 1 pressure is raised, and process 1, 2 the volume is from V1 to V2. During process 2, 3 the point V2, V3, then isothermal expansion with V3, V4, and a final that is adiabatic compression V4 to V1. Net work done equal to heat supply during the isothermal expansion minus heat rejected during the isothermal compression. So we already see that during the curve 1, 2 the heat is supplied, and process 3, 4 the heat is rejected. So we can write Q1 minus Q2 equal to MRT1 log e raised to R minus MRT2 log e raised to R. So this is for Q1 and this is for Q2. So MR log e raised to R common, we can write T1 minus T2. Thermal efficiency of the Carnot cycle equal to work done heat supply. So we can write Q1 minus Q2 divided by Q1. This is equation number 1. So put the value mR log E into bracket T1 minus T2 means this value Q1 minus Q2 divided by Q1 value, that is Q1 value mR T1 log E raised to R. So we simply put all the value of Q1 minus Q2 divided by Q1. Simplify this term, we can write 1 minus T2 divided by T1. This is our equation number 2, where T1 source temperature or maximum temperature of the cycle, T2 sink temperature or minimum temperature of the cycle. Comparing equation number 1 and 2 means this equation number 1 and this equation number 2. We can get 1 minus Q2 divided by Q1 equal to 1 minus T2 divided by T1. So that is Q by T equal to K. K is the constant. From this equation, it is clear that the heat transfer from a heat reservoir is proportional to the test temperature. It is called Carnot principle. So from this equation, we can see that Q by T equal to constant. So it is called Carnot principle. Now see the limitations of Carnot cycle. The first one, in Carnot cycle, isothermal and adiabatic process take place in the same stroke. That is, for part of the stroke isothermal process, the piston should move very slowly, and for remaining part adiabatic process is move very fast. This variation of the speed is the same stroke is not possible at the actual practice. So this is the limitation number 1. Second, it is not possible in practice to have interchangeably cylindrical head. Second limitations. Now we can see the third, that is the Carnot cycle is the hypothetically and cannot be adopted in practice. Fourth, working fluid is real gas and not a perfect gas. Fifth, perfect adiabatically heat walls without any heat loss are not practicable. Some losses during the frictions always take place, and therefore reversible processes are not possible. Seventh, working components are not weightless. And final, for heat transfer to take place, some temperature difference is required, but the temperature is a constant during isothermal process, which is not possible in practice. So these are the limitations of Carnot cycles. So in exams, the question may be asked, write down the limitation of the Carnot cycles. So you have to remember this point. So in this video, I covered assumption made in working of Carnot cycle, 4 processes in Carnot cycle, and limitations of Carnot cycle. So if you find my video very helpful, you can subscribe my YouTube channel, join us on FB page, join us on Telegram channel Engineering Guru 2020, WhatsApp channel Engineering Guru 2020. If you find my video very helpful, you can like, comment, share and subscribe. Stay on this channel. More video will become of the playlist Heat Engine.